All right, hello and welcome. If you're gearing up for the SSC CGL exam, then you know just how crucial Indian geography is. It's a real high-stakes section, right? Well, today, we're going to tackle one of its biggest topics, the atmosphere. Think of this as your personal study guide, totally focused on giving you the high-yield facts you absolutely need to know.
So let's start with a question. What's this invisible shield that's all around us, protecting us from space and, creating all the weather that shapes our entire world? Of course, it's the atmosphere. And really getting a handle on it is your ticket to acing this part of the exam. So let's dive in and break it all down.
Here's our game plan for today. First, we'll cover the absolute basics, what this protective gas blanket is actually made of. Then, we're going to take a journey, a trip straight up through all its layers. After that, we'll look at how it works as Earth's climate engine, what happens with water in the air, and finally, we'll zero in on some key atmospheric phenomena specific to India. Sound good? Let's get started.
First things first, we need to build a solid foundation. So what exactly is this blanket of gas that we're all living in?
At its core, it's actually pretty simple. The atmosphere is just this big mixture of different gases. And the only reason it all doesn't just float away into space is Earth's gravity, holding it all close. So the next logical question is, what exactly is in this mixture?
Okay, you're going to want to really pay attention to this slide. These numbers, they are classic exam questions for sure. The two big players, obviously, are nitrogen at a whopping 78% and the oxygen we breathe at 21%. But here's the one people sometimes forget. Argon. It's the third most abundant gas, coming in at just under 1%. Seriously, lock these percentages in your brain.
All right, so we know what it's made of. Now let's imagine we're hopping in an elevator and taking a ride from the ground all the way up to the very edge of space. We're going to explore each distinct layer of our atmosphere one by one. This diagram probably looks pretty familiar, right? It's our roadmap for this journey. We start right here at the bottom, in the troposphere, where we live our lives. Then we go up through the stratosphere, the mesosphere, the thermosphere, and finally, all the way out to the exosphere. But let's be real. How do you remember that specific order when you're under exam pressure?
Well, I've got a fantastic little trick for you that will lock this in your memory. Just remember this phrase, thanks so much, the X. That's T for troposphere, S for stratosphere, M for mesosphere, T for thermosphere, and X for exosphere. Simple, so effective, and totally exam-proof.
So this table right here, this is basically your high-yield cheat sheet for the exam. Let's run through the must-know facts. Down here in the troposphere, that's where all our weather happens. Simple. Move up to the stratosphere, and you've got two huge things. The super important ozone layer, and it's also where jets fly to get that smooth ride above the clouds. Then you hit the mesosphere. Think of it as our shooting star shield, because that's where most meteors burn up. The thermosphere, that's home to the ionosphere, which is what lets radio signals bounce around the globe. And way, way out at the top, you have the exosphere. That's the final frontier, pretty much merging with space, and it's where our satellites hang out.
And in between these main layers, you've got these boundary zones, the pause layers. Just think of them as transition zones. The tropopause, stratopause, and mesopause, they just mark the very top of the layer they're named after. It's a really simple naming rule that shows up all the time in those match the following type questions.
Now, here's a number that is an absolute favorite for exams, 6.5 degrees Celsius. This is the average rate that the temperature drops for every 1,000 meters you go up in the troposphere. It's called the adiabatic lapse rate, and it's a really fundamental idea in weather science.
Okay, let's shift gears. For our next section, we're going to see how this whole atmospheric machine actually works as a climate engine. How it deals with all that incredible energy blasting at us from the sun.
So here's something that trips a lot of people up. You might think we have winter because we're farther from the sun, but check this out. Perihelion, which is when we are closest to the sun, actually happens in January, and aphelion, when we're farthest away, is in July. So what does that tell you? It tells you our seasons are caused by the Earth's tilt, not how far away we are from the sun.
So what happens to all that energy from the sun when it gets here? Well, a bunch of it just gets reflected right back. And this power of reflection has a name, albedo. This single concept explains why our polar ice caps are so critical. They've got a super high albedo, acting like these giant mirrors that reflect sunlight and heat back into space, helping to keep the planet cool.
And speaking of protection, let's quickly clear up two key ideas about the ozone layer that you need to keep separate. The Montreal Protocol, that's the action we took, the big international agreement to stop using chemicals that were destroying the ozone. The Dobson Unit, That's the measurement. It's how scientists actually measure how thick that protective layer is. One's the plan, the other's the ruler. Don't mix them up.
All right, let's talk about one of the most dynamic, most important parts of our atmosphere: water. I mean, this is the stuff that makes the clouds, the humidity, the rain. It literally shapes our world every single day.
Now, humidity can seem a little tricky. Absolute humidity is just the straight-up amount of water in the air. That's it. But relative humidity, the number you always hear on the weather report, that's a percentage. It tells you how full of water the air is compared to the absolute maximum it could hold at that specific temperature. And that's exactly why hot air can feel so much more humid. It just has a much bigger capacity for holding water vapor.
So when all that water vapor finally cools and condenses, we get rain. And there are three main ways this happens. But for your exam, you need to laser focus on number 2, orographic rainfall. This is the big one for India. It's what happens when mountains, like the Western Ghats, force those moist winds coming off the sea to go up, which makes them cool down and dump all their rain. This process is the engine that drives the Indian monsoon.
Of course, rain isn't the only thing that happens when water condenses. You've also got dew on the grass in the morning, and if it gets cold enough for that dew to freeze, you get frost. And then there's fog and mist, which are basically just clouds that decided to hang out right at ground level. These are just quick, easy definitions you should have in your back pocket.
Okay, let's bring all of this home. It's time to connect these big concepts to some specific atmospheric events that are super important for the Indian subcontinent, and are, you guessed it, very common exam topics.
If you want to know the number one driver of the Indian monsoon, it's this: the ITCC. It's basically a low-pressure belt that kind of follows the sun. So in the summer, when the sun moves north right over India, this belt shifts up with it. And what does that do? It pulls in all those moisture-packed winds from the Indian Ocean. That massive shift is the main trigger for the southwest monsoon.
But what about rain in the winter? That's where something called western disturbances come into play. These are basically storms that start all the way over in the Mediterranean Sea and are carried to India by these super fast, high-altitude winds called the jet streams. They are absolutely vital for winter crops like wheat, especially in states like Punjab and Haryana.
And finally, let's wrap up with 2 famous local winds you've definitely heard of. The Loo, that's that infamous hot, dry, dusty wind that sweeps across North India in the summer. And then you have the mango showers. These are those wonderful pre-monsoon rains down south that, just like the name says, are perfect for helping the mangoes get ripe. Both are just classic examples of local atmospheric phenomena.
So there you have it. We've gone from the very edge of space right down to the local winds of the Indian plains. You now have a solid framework for understanding our atmosphere and what makes India's climate so unique. And that leaves us with one final, big question to think about. As we continue to impact this incredibly delicate system, how will these ancient patterns we've just studied, the monsoon, the winter rains, how will they change in the future? Something to keep in mind. Thanks so much for joining me.